Again, welcome to our second lectures in discrete mathematics. In the previous lectures, we discussed about propositional logic. In this lecture, we are going to talk about some few applications of propositional logic. So our main objective is to go through these 6 applications for propositional logic. The first will be, how can we use the concept here to translate English to propositional logic, English sentences to propositional logic. Also system specifications, Boolean searching, logic puzzlings, logic circuits, and AI diagnostic method. So we start with translating English sentences. Now, steps to convert an English sentences to a statement in propositional logic is 2 steps. First, we need to identify the atomic propositions. That's the simplest sentence, each sentence, and represent it using a variable or propositional variable. So when we use the term atomic, we mean the most simplest unit of an item. So here we mean if a sentence is a very one sentence. Now, after that, we determine the appropriate logical connectives. The logical connectives are what we studied in the previous lectures. That is conjunction, or the and operator, and disjunction, which is the or operator, or negation, not operator. Not operator. So let's see an example here. So as we said again, only 2 steps to translate English sentences to a propositional logic. We identify our propositional variables and we use our logic connectives. So there's an example here. If I go to Paris or to the country, I will not go shopping. Now, this is what we mean by atomic proposition. Now, I can say if I go to Paris or to a country, I will not go shopping, period. It seems like this is a one sentence. And it's a one sentence because it's one period. But it's not in atomic state or stage. We need to reduce it to the lowest unit of a sentence. So this will be, if I go to Paris, that will be 1. So after I identify this, then I will represent, if I go to Paris, to a proportion, in this case, we represent it to a variable P, or propositional variable P. To the country will be Q. I will not go shopping. That's the smallest unit of a sentence. There's no comma, no N, no or. So that will be R. So the only thing we should know here is that in order to identify atomic propositions and represent using propositional variable, we need the sentences with no or and also no end and no period. So if I go to Paris, that will be 1 because there's or, so I can't combine the 2. To the country, comma. I don't need a comma or and or period. So to the country will be 1. I will not go to shopping will be another. Now, the operators most of the time will be not, or, and the logical connectives. In these sentences, we have only or. So we are going to use or. So we can see we are using the symbol for or, which is disjunction. So first I will represent, if I go to Paris to P, or is disjunction. To the country, I go to the country to be Q, then I will not go to shopping to be R. So we can represent these sentences as if P or Q, then not R. And the symbol will be P, disjunction Q, parenthesis, implies to not R or negate R. So again, if I go to R is P, or is the logical connectives. disjunction or. To the country is Q. I will not go to shopping is R. Again, we can use any symbol or any characters here. Any characters for PQR. So the problem is we should translate the following sentences into propositional logic. Here the question said, so the sentences said, you can access the internet from campus only if you are a computer science major or you are not a freshman. So we can see the keyword here, or again, or will mean, again, our propositional connectives. We also have not to negate. And here we don't have no end. So first, the solution, we came up with A, C, and F. Again, as I said earlier, the previous example, we used PQR. We can use any character. So here we are using character A, C, and F to represent respectively. First, we can see the sentences here. You can access the internet from campus. Then you are a computer science major. Then another one, you are not a freshman or you are a freshman. So you can see that here we have, you can access the internet from campus. You are a computer science major. You are a freshman. So this is the symbol. We represent A as you can access the internet from campus. Only if, so that would be in price. In price, if you are a computer science major and we are using C, or if you are not a freshman. So freshman, not freshman represent F, not is to negate. As we said earlier, the propositional connectives here is N, or, and not. And also implication. Implication is if, only if. So that's why we see the only if here we use imprise symbol. So you can access the internet from a campus. That should be the most atomic proposition. Very simplest sentences. If only, then imprise. A computer science major, or so we represent another variable as a computer science major because or is an operator. You are not a freshman, so negate freshman. So this is what our propositional expression will be. A, only if, C, or not F. Okay, so we move to another application. This is system specifications. Here we see a system and software engineers take requirements in English and express them in a precise specification language based on logic. So we know in software engineering, one of the software development cycle or stages is to collect a requirement from the users or the stakeholders of the project. So this requirement can be two types: functional requirement, which are the sentences, or in this case, what the system will be doing. Non-functional requirement will be the quality of the system. So this will be in the sentences, and our goal now is to convert it. So example here given, expressed in propositional logic, the automated reply cannot be sent when the file system is full. So this is again a system requirement, and this will be a functional because how the system will operate, the task, the function of the system. So we can see the solution here. One possible solution means let P donate the automated reply can be sent, and Q donate the file system is full. Because here we have the automated reply cannot be sent when the file system is full. So something like a when shouldn't be in our, again, atomic proposition. So we can say the automated reply can be sent. Q, the file system is full. So the reason why we are representing Q as can be sent, because not is negation. So we can have not P. So if P is the automated reply can be sent, then negate P will be the automated reply cannot be sent. So that's why we can see our propositional logic expression here. Q means when the file is full. So now we are saying that when the file is full, we cannot send, or automated reply cannot be sent. So we use negation P. P represents the automated reply can be sent. And the sentences said the automated reply cannot be sent. So we are using not P. So this is a consistent system specification. The definition is that a list of propositions is always consistent if it is possible to assign a true values to the proposition variables so that each proposition is true. And we'll say this is consistent. So exercise here, are these specification consistent? Let's look at it. The first one, the diagnostic message is stored in a buffer or it is retransmitted. A diagnostic message is not stored in the buffer. If the diagnostic message is stored in the buffer, then it is retransmitted. So this will be the solution. First, we let the P donate as the diagnostic message is stored in the buffer. Then we say Q, the diagnostic message is retransmitted. So the specification can be written as P, because we can see the diagnostic message is stored in the buffer or it is retransmitted. So we say P or Q. Then second, the diagnostic message is not stored in the system, so it will be not P. And the third, if the diagnosis system is stored in the buffer, which P, then it is retransmitted. So it to be retransmitted. So that means P, then we do, if P, then Q. We should know here that we say the diagnostic message is transmitted, and also that will be Q, then P, let Q donate, the diagnostic message is retransmitted. So that's why we say if P, then Q, because then it is retransmitted, so then Q. And P again is the diagnostic system is stored in the buffer, or it is retransmitted, so P or Q. The diagnostic message is not stored in the buffer, so this will be only not P, because P is the diagnostic message is stored in the buffer is P. So not stored in the buffer is not P. Then the third one says if the diagnostic message is stored in the buffer, which is P, then it is retransmitted, so it will be then Q. So if P, then Q. If P, then Q. Now, what if the diagnostic message is not retransmitted, is added? Now we are adding not Q, because we said transmitted is Q, so not retransmitted is not Q. But again, there's no satisfying assignment here, so the specification is not consistent. So let's look at another application, logic puzzles. So here we say if an island has two kinds of inhabitants, the knights who always tell the truth and the knaves who always lie. Here say you can go to the island and meet A and B. A says B is a knight and B says the two of us are of opposite type. So example, what are the types of A and B? Remember A said is what? We said A says B is a knight, and also B says the two of us are of opposite types. But here we have the island has two kinds of inhabitants: the knights who tells again the truth and knaves who always lie. So if A says B is a knight, then B always tell the truth. Now if B says the two of us are of opposite type, then if B tell the truth, then A tell lie. If A tell lie, then B tell the truth. So what are the types of A and B? So solution, let P and Q be the statement that A is a knight and B is a knight, respectively. So then, not P will represent the proposition that A is a knave, and not Q means B is a knave, because A is a knight, B is a knight. So not A will be knave, not P will also be knave. Now we say if A is a knight, then P is true, since knights tell the truth. Q must also be true. Then we have P and not Q. So P and not Q, because they're opposite. The whole trick here is that we say the two of us are of opposite. So if it's not P and Q, so that's why we have a not P and Q, or P and not Q. In this case, again, we are going to use or, either two. Now the P and Q are opposite. So you have P and not Q, or Q and not P. Again, the opposite V from our previous lecture is and, or conjunction. And the V is or disjunction. So this is a logic puzzle. If A and B are opposite and A is P and B is Q, then it will be A and not P, or P and not Q. Again, P and not Q, or Q and not P. And the next application is logic circuit. Logic circuit, we are going to study this in depth in the coming lectures. It's a chapter by itself. So in logic circuit, we're going to start with what is a Boolean algebra, how do we design combinational circuits with the logic gates. We talk about different logic gates. And also this is an application of propositional logic. So here we have electronic circuits. Each input and output signal can be viewed as 1 or 0. Well, this is again binary number or machine language. 0 represents false and 1 represents true. So in a digital circuit or even computer language, it's only two states, 0 or 1, 1 or 0. So complicated circuits are constructed from these three basic circuits called gates. Again, we have the inverter is the same concept as negation or NOT gate. Then OR is the same as disjunction. It's addition or gate. That's why it's called OR, disjunction. Then N is the same as conjunction, propositional logic operator. So we know that N means product. So this means if input is P is 1 and Q input is 1, then the output will be 1. If P is 1 and Q is 0, the output will be 0, because 1 times 0 is 0. 0 times 1 is 0. If both of them are 0, the output will be 0. When we say 0, we mean it's false. And when we say 1, we mean it's true. In OR gate is plus. So true will give us true. True false also give us true, because 1 plus 0 is still 1. In N is product, so 1 times 0 is 0. So we may discuss this more detail in the coming lectures. And another application is the diagnosis of faults in an electric system. And here we say the AI stands for artificial intelligence. And this is the foundation of computational agents. So AI example here. Here we say we need to represent a propositional logic, the features of a piece of a machinery or circuitry that are required for the operation to produce observable features. This is called a knowledge base. The concept of knowledge base is used a lot in the earlier days of AI, before machine learning and data mining. A knowledge base, I can build an artificial intelligence system, AI system, or sometimes we use the term expert system. In today's technology, we use data analysis or data mining, data science, and then we use the data to build a system with a learning algorithm to build a system, the model. Then we use it to again perform our tasks. But in the earlier days, we design an expert system, which is a knowledge-based system. So this means we need an expert, a human expert, that's a medical doctor, who is going to tell us all the requirements for the system to make the right decision. And these are called the knowledge base. And mostly it's if-then rules, if-then rules. So we can also use the propositional logic concept on these applications. So we have electric system diagram. Here we can see we have a switch. So the lights represent L1, L2, which are right here, the blue. And we have WO up to W4, which represent the wires. So we can see that the wire WO connect the one light bulb to the switch S2. So S1, S2, S3 are switches. So this is electric diagram with switches. We have 3 switches, and we have wires connected to between the switches and also the light bulbs. So we need to represent our common sense understanding of how electrical system works in propositional logic. So for example, we have L1 as our light. Now we say if L1 is receiving current, then of course it's going to light, which will be controlled by the switch. If I turn off the switch, the L1 is not going to receive no more current and it will be off. So we have a propositional logic here saying that light L1 and leave L1 and OK L1, then we are going to have a light on L1. Also, if W1 has current and switch S2 is in the up position, then S2 is not broken, then WO has a current. So this means the switch is on, and we can go back to the circuit. If switch S2 is on, there will be a current between between S2 to L1, which is the WO. Now, if the switch is off or is open, then there's no current on WO. That's between S2 to L1. So what we are doing, we are generating the knowledge-based system of this electric circuit. What conditions will make the 2 lights on, and what condition will make the 2 lights off. And that's what we are doing here. So then next one, we said that if W1 has a current and S2 is in the up position and S2 is not broken, then WO has a current because the switch is closed between WO and S2. The W is the wire between L1 and also S2. So this is the sentences. Now we can write in propositional logic. We have live W1 and ops S2, which means it's on, and OK S2 is not spoiled. Then there's a life on WO, or the current in WO. So we can say that representing electrical system propositional logic. We have the electrical system, but we write in sentences the conditions that will make the electric system have a current or not having a current. And we are going to state those conditions down using propositional logic and connectives logic operators. So this is the example of the knowledge base for the whole electric diagram. So life outside, light L1, L2, life on leave W0. If there's W0, there's current, then light 1 will light. And when you go to the circuit, we can see that if WO have a current, the L1 will light. The bulb will be on. So and that's the rule here. Now the same thing, if there's a current in W1 and W2 is on, is up means it's close, it's on, and W2 didn't spoil, is good, then there will be a current on WO. So the same thing based on the circuit. If life W2 and down, this time we say S2 is down, and also S2 is okay, then we may have life on WO. Now we can see the circuit and see if this rule hold. We can see that W2 is down and S2 is okay, and S2 is live. So we may, so where's W? This is W2. W2 is down, yes. You can see W2 is not connect, is down. But S2 is okay. So we may still have a light, or WO maybe having current or life. So again, this is the concept of electrical system in propositional logic. And these are the knowledge base again. So we have another observation here. Observation need to be added to the knowledge base. Very important. So both the switches can be up, which means S1, S2 is up, or both lights are dark, which means not light L1, not light L2. And we may use this in our, for example, the last one we say there's light in L2 and L2 is live and L2 is okay, which means there's a power is live and it's okay. So this means then the L2 will be light, it will be on, the bulb will be on. Now if live outside and CB1 is okay, then there will be live on W3. So again, this is CB1, outside power. You can see if outside power is on and S1 is on and S2 is on, then they'll set WO, there will be power. Or right now CB1 is on, W3, if S3 is on, W3 will be on and there will be light on L2. So these are some of the few applications in, again, propositional logic. The next is the diagnosis. So here we can assume that the computers are working okay, unless we are forced to assume otherwise. These atoms are called assumable. So most of the condition here, we are assuming it. So here we have OKCB1, OKS1, OKS2, OKS3, OKL1, OKL2. Represent the assumption that we are assuming the switches, the light, the circuit breakers are okay. Now, if the system is working correctly, all assumables are true. The observations and the knowledge base are consistent. So the augmented knowledge base is clearly not consistent with the assumable are all true. The switches are both up, but the lights are not light. So some of the assumables may be false. This is the basis for method to diagnose possible faults in the system. So these are some, here they say we should see artificial intelligence, Foundation of Computational Agent by David Poole and Alan Markwood's 2010 textbook. So for details on this problem and how the method of consistency is based on diagnosis can determine possible diagnosis for the electrical system. Here we have approach here, the 7 possible faults, or I'll use the term rules here. At least one of these must hold to have a fault. So if the circuit breaker 1 is not okay, then there will be no light. Both switch 1 and switch 2 are not okay. Problem. Switch 1 and light 2 are not okay. Or both switch 2 and switch 3 are not okay. Both switch 2 and light 2 are not okay. Both light 1, switch 3 are not okay. And both light 1 and light 2 are not okay. So I'm going to end the lectures here. So in these lectures, we went through some few examples on applications of propositional logic. So as we said in the previous lectures, the propositional logic consists of at least 2 major things: the variables and also the propositional logic or connectives. That is the and, or, and not operators, which we use the term conjunction, disjunction, and negation. So we use these 2 things, the propositional variables and propositional logic, again to translate the sentences, set up the knowledge-based system in AI, and also electric circuits. So again, wish everybody the best, and we meet in the next lectures. Thank you. Bye.